All right, we're going to continue with our look at characteristics of a graph, starting with the idea of even versus odd functions. So that's our first type. We have an even and an odd. Now, graphically, what makes something even versus odd, it kind of refers to the symmetry in the picture. So let me kind of get a typical even function versus a typical odd function. Now, what do you notice is what do you notice is different about the two pictures versus what do you notice is sort of consistent about the two pictures? Do you notice that there's mirror images connected in both? That in both even and odd functions, you can see that half of the graph looks like the other half, and then what the other half does is sort of different. So with an even function, one idea we might get associated is that the left half looks just like the right half versus the first quadrant looks just like the third quadrant, sort of feel to it. Okay, so when we describe this, we say that even functions are symmetric to the y-axis, which another fancy way of saying we're going to fold it over the y-axis. So if you imagine you took a piece of paper and folded it from left to right, you'd get the same image on top of itself. In an odd function, we refer to that as symmetric about the origin. And if you like that folding idea, then you'd have to fold it twice. So you fold it over the x and the y-axis at the same time, and you should notice the same image. Okay, algebraically, if I want to determine if something is even, then f of negative x should be equivalent to f of x. This kind of goes back to, let me kind of go back to the graph. So if I look at any ordered pair on the right side, I should find a mirror point on the left that have the exact same numbers, and the only difference would be a sign in them. Alright, so f of negative x equals f of x for all x in the domain, then the function is considered even. And the idea here is same signs on y's. If we get the y values have the same signs, then we know they're even. In an odd function, so if f of x is going to equal negative f of x for all x in the domain, then the function is odd. So going back to the graph, if I take any ordered pair in one quadrant, I should find a mirror point in the other where the x's would be the same, but the y's would be the exact opposite of each other. So opposite y's. All right, so the question then is, if I give you an equation, how does one tell whether it's even or odd? Or none of the above, actually. And it goes back to that negative x. So if I take f of x and I replace the x with negative x. So let's do that. Okay, so 3 something squared plus 1. I want to fill the hole with negative x. So I get, if you square a negative, you get a positive, so I get 3x squared plus 1. Okay, now, how does that compare to the original? They are the exact same. So f of x in this case is equivalent to f of negative x, and that is textbook even, which means this particular function is an even function. All right, in the next example, so same thing, we're going to do f of negative x and see what we get. So I want 4 times something cubed minus something. And what do I fill the hole with? with negative x. Alright, so if you cube a negative, you actually get a negative as a result. So negative 4x cubed plus, because two negatives make a plus, plus x. Now, compare that to the original. How do those two look? Well, they look exact opposites of each other, actually. We went from positive 4x cubed to negative 4x cubed, went from negative x to positive x. Okay, so what we've shown is that f of negative x is the exact opposite of f of x, which means that it is an odd function. Alright, last one of these algebraic ones. So again, f of negative x. So I want something to the fifth plus 1, and I'm going to fill the hole with negative x. Alright, what is negative x to the fifth? Well, again, it's to the fifth power. It's an odd exponent, so a negative is going to come out. And let's compare that to the original. And this is where we sort of get a, that's interesting. So with the x to the fifth, we do have opposites, a negative x to the fifth, but the plus 1s are the same. So it doesn't quite fit either pattern, and so this is where neither comes in. So if it's not exactly even or exactly odd, it's neither of them, so we can't call them even or odd. All right, graphically. Okay, so let's look at our graphs here. Let's see. So I can see that there's a sort of mirror image, and I can see that there's the left side and there's the right side, and they in fact match each other. So this is symmetric about the y-axis. Which is by definition an even function. Okay. In the next example, I can see there's a pivot point, and then when I look very carefully, I can see that the second quadrant looks just like the fourth quadrant. So it has that, if I reflect it twice idea, then I get the same image. So this is symmetrical about the origin. So it's an odd function. Alright, this last one, I can see there's this pivot image, and I can see the top part, it matches the bottom part. So I definitely can say that it's symmetric about the x-axis, but it's not one of our special cases, so it's not even or odd. And a lot of times we sort of overlook this idea that even in odd or function terms, is that last one not even is it even count as a function? And no, if you do the vertical line test, it's not even a function. So even though it does exhibit symmetry, so it is symmetrical about the x-axis, it doesn't even count as a function, so we can't even call it even or odd if we wanted to. Alright, so this brings us to what's called a piecewise function. So let's take a look at that. A piecewise defined function is a function that is defined by more than one equation over a specified domain. Okay, piecewise meaning we've got more than one equation that's defining this thing, and it's in, that's where the idea pieces come from. Well, we're actually familiar with this. A lot of us have cell phones, and we're familiar with cell phone plans, and a lot of cell phone plans have restrictions on you can have so many minutes up for a certain cost, and if you go over that, then there's another cost associated with that. So let's take something that makes a little bit more sense to us. So for this particular cell phone plan, we're going to pay 20 bucks for the first 60 minutes and then 40 cents for each additional minute. So what would the cost look like? Well, it's going to cost me 20 as long as I talk anywhere between 0 and 60 minutes. Now, if I go above 60 minutes, it's going to cost me a little bit more, right? So let's think about this. It would cost me the original 20 plus each minute beyond the 60. So that's the 0.4, so 40 cents. And I want to subtract off 60 from the number of minutes that I actually use. And this would be anything that's bigger than 60. Okay. Now, we have, over here, we have what are called domain restrictions. Okay, these tell me when to look at each piece of my function. So if it's between 0 and 60, I'm going to look at the top equation, which in this case happens to be 20. And if it's, sorry, I didn't realize I didn't put a t there. If it's anything bigger than 60, I'm going to look at the bottom equation. Okay, so the domain statement tells me which equation to look at. And it doesn't make sense to have two y values associated with each x. It's still a function. Okay, so let's look at some values of this. So let's say I talk 30 minutes. How much is that going to cost me? Well, 30 is between the 0 and 60, so according to it, it's just 20. So that makes sense. It's just going to cost me 20 bucks, just my plan. Nothing special there. Well, what if I talk 120 minutes? 120 is more than 60, so that tells me to look at the bottom equation. So that's 20 plus 0.4 times 120 minus 60. All right, so I want to get my calculator handy for this one. Well, maybe. 20 plus 0.4 times 60, let's see, 4 times 6 is 24, so 240 with the decimal puts it at 24. And if you want to confirm that using your calculator, that's fine. So, according to this, I would spend $44 if I was to talk 120 minutes. Alright, so what do we actually need to do if I want to evaluate or eventually graph these things? Let's start with evaluating. So to find a functional value whose piecewise defined function, you must look for the domain the function value belongs in. In other words, look at where the x is, and what do you look at the top, the middle, the bottom, where are you looking? Then substitute that value into this corresponding equation. Okay, so here we got some practice here. F of negative 3. Alright, so is negative 3, is that less than 0 or greater than or equal to 0? Hopefully, we got that it's less than. So I want 6 with a blank minus 1, and I'm going to fill the blank with that negative 3. So negative 18 minus 1, which gives me negative 19. So there's my function value for it. What about f of 0? Well, where do I find 0? Do I find that in the top or the bottom? And looking at my domain statement, domain x greater than or equal to 0, so I want that in the bottom. So fill in the blank with the 0. So 7 times 0 plus 3 is 3. There's that one. And then the last one here, f of 4. So where do I find 4? It's at the top or the bottom equation. And 4 happens to be bigger than or equal to 0. So it's bigger than 0. So that means I'm going to use the bottom equation to find f of 4. Alright, so we want to fill the hole there. So 7 times 4 is 28, plus another 3 puts us at 31. So those are those functional values.